All right, so today I am happy to introduce Rob Fovell as our seminar speaker. He's visiting us from the University at Albany, State University of New York, and he's visiting us through the DTC visitor program, where he's working with the hurricane team to assess the sensitivity of various PBL schemes within the operational hurricane WRF model. So I think he's got some really interesting results to show today, and so without further ado, I guess I will hand it over to you, Rob.
Okay, thank you. Okay, is this working? Yep. All right. Okay, so one thing I have learned sometimes the hard way is that my voice projects. So I actually don't think I need a microphone. I think that you could probably hear me in FL3, but anyway. So thank you for the invitation. This is the second DTC visitor presentation that I've done, but the first one was only to DTC people. It wasn't advertised a little more widely. So once I learned that this was disseminated a little more widely, I decided to give a broader overview of the reason why I was interested in boundary layer mixing, because I haven't been able to present the first third of this material here before. So there's something more than boundary layer mixing here. But in case you start wondering somewhere around the 10-minute mark, where's the boundary layer stuff, it is actually eventually coming. So here's a quick overview. One of the things I got interested in the last number of years is how models determine the size of tropical cyclones. Tropical cyclone size is an important metric because it influences things like motion through the beta drift. It also influences the storm surge and who gets warned when and why. Two major influences on tropical cyclone size that have emerged from our research are cloud radiative forcing, which I'll call CRF. Cloud radiative forcing is the interplay of microphysics and radiation, and planetary boundary layer mixing, primarily moisture. So the way these work is indirectly by encouraging outer core convective activity. I'm going to try to demonstrate that using what I call semi-idealized models or semi-idealized simulations. These are simulations that take a model that would be used in operations but dramatically simplify the initial conditions in order to make the problem a little more tractable. Okay, so I'm going to specifically refer to these two papers, which were published in 2014 and 2017, both in JAS. Okay, and I also want to assess how well PBL schemes reproduce some available observations. So I'd like to start with one of my favorite sayings, which is attributed to Albert Einstein: make things as simple as possible, but no simpler. I've been using this for years, but recently I've learned that Einstein actually never said this. Okay? Actually, he conveyed this idea in a more complex fashion, and someone else had to slim it down to this. So with that, here's some background. Okay, so here's my semi-idealized experiment. Basically, in the mid-2000s, when the hurricane seasons got more interesting, at least as far as Florida is concerned, and WRF version 2 came out, and I found it usable, which actually means I managed to get the damn thing compiled, I started studying tropical cyclones. Okay, because I thought it was a nice problem to look at. I quickly realized if I manipulated things like microphysics and cumulus parameterizations, I can get sometimes substantially different tracks, even in relatively short periods of time. And I looked through the literature, I didn't see very much about that, so I thought that this was an interesting topic to try to explore. Okay, but real data simulations are so complicated. You have gradients of sea surface temperature, you have wind, shear, troughs, ridges, land, coastlines, whatever. So in order to try to make this as simple as possible and no simpler, what I designed is what I call the semi-idealized experiment. Relatively high resolution in order to eliminate the cumulus parameterization part of this. So these are using the real data WRF ARW at 3-kilometer resolution out to 72 hours. But I've made the sea surface temperature uniform. I'm initializing with a single tropical sounding. So there's no initial flow, there's no wind shear, and also no land. Okay, so you kind of see land here, but I sketched land on this particular plot in order to give you a sense of scale. Okay, and what you're seeing here, the results are the tracks over a 72-hour period from 7 different microphysics schemes that were available in WRF at the time, starting with one initial condition. So what we're seeing is those tropical cyclone starts here, and they're all moving towards the northwest owing to the beta drift. Okay, but after about a day and a half or so, the tracks start diverging. Some of them turn towards the north, some of them continue towards the northwest. One of them breaks out and runs for daylight, and it would end up in Oklahoma if there were an Oklahoma in this model. Okay, but basically we're seeing the evolution or the development of different tracks here as a consequence of using different microphysics schemes. So what's going on here is microphysics schemes yield different amounts of various kinds of hydrometeors. They result in storms that have different diabatic heating patterns. They have different symmetric and asymmetric wind structures, and they have different intensities and clearly, as seen in the plot, different motions. Okay? So at least part of the reason, and probably a large part of the reason, that the storms move in different fashions and in different speeds is because they develop different outer core wind profiles. And that is being illustrated here. The horizontal axis is radial distance from the eye out to 800 kilometers. The vertical axis is wind speed at 850 millibars. Like a lot of my plots, I am basically taking the storm, I am following it over a 24-hour period, I am averaging over that 24-hour period, and then I am averaging azimuthally around the storm. And these are the wind profiles that result from that. So 3 of the microphysics cases are shown here. Clearly, the wind profiles are different. Because I'm showing you such a large radial extent, it may surprise you that the difference from the smaller to the larger is 70%. So what I'm highlighting here is the radius of gale force winds, 34 knots or approximately 17.5 meters per second. Okay? So basically, these storms are producing, over a relatively short period of time, rather different wind profiles, and these wind profiles are influencing how the storm moves. That's illustrated here in this classic study by Fiorino and Ellsbury from 1989. They took a vortex in a barotropic model, and they imposed 3 different outer wind profiles. So this is wind speed versus radius. There are 3 wind profiles, A, B, and C. They only vary beyond about 300 kilometers. Okay, but basically these are the tracks that result from that. So this is longitude by latitude. Track A, with the largest wind speed in outer radius, produces a tropical cyclone that moves very quickly towards the northwest. Looks a lot like the one that's labeled K there. The other 2, these wind profiles are actually very subtly different at the beginning, but they're diverging in a manner that is reminiscent of some of these other simulations there. So at least part of this is due to the fact that the microphysics, for reasons that I haven't explained yet, but I hope to explain to you, are basically producing different outer wind profiles. Okay? Now, one of the things that makes microphysics schemes different, even schemes that are trying to simulate relatively the same thing, that they have lots of knobs and collision efficiencies and drop size distribution parameters and fall speed parameters and things like this, and this varies from scheme to scheme. And as a consequence, some schemes will produce more of certain kinds of species than others. So basically what I'm trying to show in this plot is basically there are 4 different microphysics schemes here. It doesn't really matter which 4 they are. And this is for part of the storm, showing that lots of the condensation is in the form of graupel, okay, particularly in this scheme. And in the other schemes, they tend to produce more ice than snow or more snow than ice. And this matters because these particles have different sizes, they have different densities, they have different fall speeds. Okay, but to my surprise, I discovered that if I turned off cloud radiative forcing, the interaction of hydrometeors with radiation, it didn't matter how much graupel or snow or cloud ice a microphysics scheme produced anymore. Okay, so basically I discovered this by going through the through the name list, going through the model, trying to make things as simple as possible, but no simpler, and trying to basically see what can I possibly turn off. And I looked at the cloud radiative forcing, I looked at the diabatic forcing that was associated with that, and I thought there is no way in heck this is going to make a difference because it's just really too small. But simulation after simulation came out to be practically exactly the same thing. Not only do they have the same track, they have the same wind profile, so they have the same beta drift and everything else. Okay, so the microphysics schemes are still producing different amounts of different kinds of hydrometeors that fall at different fall speeds, but it doesn't matter anymore because what made the microphysics relevant, interaction with radiation, has essentially been removed. So I'm going to call these simulations CRF off. In these simulations, radiation is still on, clear sky. The sun is still up half the day. There's still long wave radiation, but the clouds have been treated as transparent to radiation. So as you can imagine from what I showed you previous, if we look at the 10-meter wind profiles here, what we're seeing here is radius versus 10-meter wind profile. This is for CRF on. This is for the blue dashed line is for CRF off. I'm highlighting here the 34-knot wind radius, 74% larger going from smaller to larger. So it's making a big difference in the size of the wind field in a relatively short period of time. Okay, and not just at 10 meters, but also through the entire troposphere. These figures show, again, simulations over the last 24-hour, average temporally and then average azimuthally, radius out to 350 kilometers, height up to 18 kilometers. And what's being shown here in the colored field is the average radial wind field. Blue is in, red is out, and superimposed with the contours are the tangential wind field. And I've highlighted here the 20 meter per second contour because that's approximately the radius, that's approximately the gale force wind. Okay, so what we can see in this case is the CRF on simulation is actually significantly larger than the CRF off simulation, not only at 10 meters, but through the entire troposphere. So what is this cloud radiative forcing field? What does it look like? Okay, and so I'm going to show you this. Now, I forgot to tell you that I'm going to show you results from WRF ARW, HWRF, and CM1 run in an axisymmetric mode. So I have now, in less than 10 minutes, shown you 3 different models. Okay, because I'm kind of treating them as fungible. Okay, so these are simulations from CM1 running an axisymmetric model or mode. The horizontal axis is radius out to 300 kilometers. Vertical axis is height up to 18 kilometers. The colored field is condensation. Averaged over 3 diurnal cycles after the storm has become mature. It's a log 2 scale, but we're basically seeing what the central dense overcast looks like. And at the top of that overcast, we see cloud top cooling. That's what the dashed contours are. And within the cloud, some warming. This is net radiative forcing, clear sky, long wave, short wave, CRF, all averaged over 3 diurnal cycles. Okay. The cloud top cooling is about 7 Kelvin per day. It's larger at some times. It's much smaller at other times. This is an average over the 3 diurnal cycles. 7 Kelvin per day is not very much, but it's much larger than the warming within the cloud, which is about a degree or so, or a degree and a half at a maximum. So we have this particular pattern, cloud top cooling, warming within the storm. This is an average over a period of 3 days. Okay. The results look similar in ARW and in HWRF with different microphysics, different radiation schemes. They're quantitatively different, but they're qualitatively similar. Now, what you're looking at is an average, as I said, over 3 days. It does not look like this at any instant of time very much. And I'm emphasizing that by showing you this animation, which is showing you hourly snapshots of condensation and net radiative forcing through this 3-day period. So all of these pictures that you're seeing now are averaging together to produce that particular field that you saw in the first slide, in the last slide. Okay, so what you can see here, actually, there's a lot of variability with respect to time. There's clearly a diurnal cycle, particularly with respect to the net radiative forcing at the cloud top. Okay? There's also a expansion and contraction and a general expansion as a function of time. But if I took all of these fields together and I averaged them, it would look like this, which is basically the same picture I showed you 2 slides ago. Okay? So this is when cloud radiative forcing is on and when cloud radiative forcing is off. And I'm inviting you to see that basically the cloud radiative forcing on simulation is significantly wider than its CRF off counterpart, even though they started with the same initial conditions. All of that variability might be important in some applications, but is it important to basically explain the difference in the storm size that we're seeing between CRF on and CRF off? The way I can test this is to basically take this field that you're seeing here, which again doesn't look like this at any particular instant of time. It varies with time, but this is an average over 3 days, and pull that out of the model, turn the radiation off, and impose this radiation field as an external forcing. An external forcing that is now independent of time, independent of convective activity, independent of anything else. And if I do that, I'm going to call that CRF fixed, I get a field that looks like this as far as condensation. What I'm hoping you see is that this looks a lot like this and a lot less like this. Okay? So the contoured field, of course, is exactly the same because it is an average here and it is an externally imposed forcing here. But starting with the same initial conditions, starting at the initial time, I'm imposing this radiation field, and this radiation field is essentially giving me this cloud shield that is significantly wider than this. Because I'm now imposing the radiation field as an external forcing independent of time and independent of convection, it's also easy to separate the influence of the cloud top cooling and within cloud warming, and I'm going to do that here. Here's the simulation with CRF fixed, but just keeping the cloud top cooling. We can see actually the cloud top cooling isn't really doing anything as far as expanding the wind field is concerned, or the condensation field is concerned. It's the within cloud warming that is doing that, okay? So basically what I'm emphasizing is this. My explanation for this that we advanced in this paper, which you probably can't read because it's down at the bottom of the slide, but long wave warming is provoking gentle lifting. This lifting is very small, but it's persistent. And it operates over a long period of time. It operates over a deep layer. And this is gently lifting air to saturation. Once air reaches saturation, convection takes over with its much larger diabatic forcing, and in a Sawyer-Eliason sense, what the convective forcing is doing is expanding the wind field. Okay, so before I leave the CRF topic completely, I want to show you one more experiment which asks the question, does the cloud radiative forcing actively control the storm size? So what I'm showing you again is the same picture you saw previously, but now I'm showing you a much larger radial extent. But because we're imposing this as an external forcing, it's a simple matter to change its scale, increasing it or decreasing it by 50%. So I'm going to start these 3 simulations at the same time with the same initial conditions, except I'm imposing 3 different radial forcing patterns as far as the cloud radiative forcing is concerned, and basically it results in this. When the cloud radiative forcing field is allowed to be quite wide, the storm is basically quite wide as well. When the cloud radiative forcing field is significantly confined and not allowed to expand, the storm never becomes very large. So what we're seeing here is that I'm demonstrating there is a positive feedback between the cloud radiative forcing and the storm size. What is actually happening in the model is this is eventually becoming this, is eventually becoming this. Okay, and that's happening because the outflow is advecting hydrometeors outward. The hydrometeors are carrying the signal of the cloud radiative forcing, helping this gentle lifting, leading to convective activity that expands the wind field. But in this case, when I'm imposing the forcing, the cloud radiative forcing, it doesn't matter if the outflow is advecting hydrometeors outward or not, because the cloud radiative signal is disconnected from the hydrometeors because it's externally forced. So the storm actually never becomes very wide. And I think you can imagine that if I showed you the wind fields here, the wind fields from these same cases are actually quite different. The top is 3 times larger than the one at the bottom, okay? So let's return to the HWRF model, okay? And I showed you this picture before, 10-meter winds with respect to radius, with the cloud radiative forcing on, other things being equal, being significantly wider than cloud radiative forcing off. And now I'm going to show you what happens when we use the radiation scheme that had been used in HWRF for most of its lifetime, okay? So that is the red curve here, and we're seeing that the red curve is actually very similar to CRF off. So what happened was I submitted a hurricane forecast improvement program proposal, and if you look at my proposal, there were the letters WRF never followed the letter H. I didn't mention HWRF at all in that proposal, but they said, we're willing to fund you if you use the HWRF model. So I said, okay. So I started using HWRF, which I had not used previously. And the first thing I wanted to look at is what does the cloud radiative forcing field look like? Because I had been studying that in WRF ARW. And to my surprise, I found there was no cloud radiative forcing in HWRF whatsoever. So it was basically treated. It had radiation, it had clear sky, long wave, and short wave, but there was no cloud radiative forcing. It was treating clouds as transparent to radiation. So clearly that was a bug. Okay, and what that bug was doing, other things being equal, was resulting in storms that were significantly narrower. So let me show you some recap regarding this. We showed that long wave warming within the cloud leads to gentle ascent above the PBL, enhancing the outer convection and expanding the wind field. It's a positive feedback. It's one of the things that makes microphysics important in tropical cyclone simulations because it helps microphysics schemes basically differentiate amongst each other. The operational HWRF model's radiation scheme was lacking effective cloud radiative forcing. That was a bug. Okay, so we reported that bug and they tested trying to fix that and found that the forecast got worse. Okay, so you've been around the block a few times, you know these things happen, and because this basically led to our first DTC HWRF project, which was back in 2014, trying to figure out why. Okay. So finally, that leads to talking about the boundary layer. So what we had quickly determined that what we felt was explaining the problem, cloud radiative forcing helps make the storm wider, okay? There was no cloud radiative forcing in HWRF. Once that bug was fixed, the storms got really big. So something else is also influencing the storm size, and suspect number 1 was boundary layer mixing, okay? So the HWRF boundary layer scheme that has been used for a long time is basically a K-profile scheme. It's called the HWRF GFS PBL scheme. And this goes back to Trone and Mart 1986 and previous papers. And what they are trying to do is within the PBL, they're trying to basically model the eddy mixing applied to momentum or heat or moisture with an equation that looks like this. Okay, so K sub M is the eddy mixing. Kappa is von Karman's constant, usually 0.4. W sub S is a velocity scale that varies amongst similar schemes, but it usually conveys information relating to the surface layer. P is a profile shape constant, but basically gives you a nice profile that looks like this when it's set to 2. And H is the boundary layer depth, okay? So basically the way these schemes work is they try to determine what H is. Once they have H, basically everything follows from this particular equation, and also everything scales with H, so that if we find a larger boundary layer depth, the maximum mixing is larger, and it's located at a larger altitude, and it extends over a greater depth. So everything is basically scaling with H. The way these work is a first guess at the PBL depth is going to be determined by computing a Richardson number, basically stability divided by shear, between the surface and a given level, and comparing that to a critical Richardson number, which varies amongst schemes. Okay, so if you use a larger critical Richardson number, you're going to end up with a deeper depth. Okay, now it's been known for a long time that the HWRF model produces way too much mixing, and that's demonstrated in this figure, which comes from Gopal et al. 2013. The horizontal axis is wind speed, the vertical axis is eddy mixing, and the purple X's are derived from observations published in Zhang et al. 2011. So what they did is they took aircraft observations and they used that to try to calculate what the eddy mixing was at 500 meters above sea level. Okay, so at 40 meter per second wind speed, they found observations to look like this, K(m) varying from 40 to about 120. You can see by looking at the purple X's that generally higher wind speeds were associated with larger values of mixing. But the gray dots are what the HWRF model was producing with the HWRF GFS PBL scheme. And you can see that at 40, 50, 60 meters per second, the amount of mixing that was being produced was really, really excessive. So as a first attempt to try to address this, what Gopal and al. Did is they took this equation I showed you previously and they tacked on a damping factor, which they called alpha. What alpha is an attempt to do is take the mixing that's being produced by this scheme and reduce it, make it something that fits a little better like these observations. So if alpha is set to 0.25, we got eddy mixing from the HWRF model, the gray dots, that looks a lot more like the observations. So in the back, you can't see that, but you have to just trust me, okay? Right? So that's with value of alpha equals 0.25. While they showed that 0.25 fit the observations very well, operationally, they chose a much larger number because this is the value that enhanced or maximized the forecast skill. So this was adopted into the HWRF model, and hurricane forecasts improved as a consequence. Now, this was also shown in Gopal's paper, but basically alpha strongly influences the inflow intensity and the inflow depth, and that's what's being shown here. The horizontal axis is radius scaled by the radius of maximum wind. So where there's the radius of maximum wind is here. This is twice and this is 3 times the radius of maximum wind. The vertical axis is height up to 3 kilometers above the sea surface. The colored field is inflow. Blue is inflow. The bluer, the stronger the inflow. The black contour here is the level at which the inflow is reduced to 10% of its maximum, which has been used as a proxy for the depth of the inflow layer in prior studies. When alpha is set to 1, that means there's no damping whatsoever, the inflow is weak and it is very deep. But as we scale towards 0.25, which was indicated in Gopal's paper, the inflow is now much shallower and it's much stronger. Okay? So it has a big difference on the storm strength and depth of the inflow. It also has a big impact on the width of the storm. I'm showing you now radius versus height simulations averaged over the last 24 hours, averaged azimuthally in a circle of water vapor mixing ratio. And we can see that the absolute humidity is largest within the core. It decreases upward with height. It decreases radially outward. This is for a simulation with a larger value of alpha, which was used in operational model, and a smaller value of alpha, which results in weaker mixing. And these fields look fairly similar, but if you have sharp eyes, you can see there is a difference. And I'll subtract the two in a second after I show you what the mixing fields look like. So the mixing fields look like this. The maximum mixing is at about 500 or 600 meters above the sea surface. It decreases downward and upwards because of this structure. It decreases radially inward and it decreases radially outward, but the big difference between these two is the weaker mixing produces about 1/3 of the eddy mixing that the stronger mixing does. So now I'm going to take these fields and I'm going to subtract them, and we have something that looks like this. Subtracting the contour fields leave a mixing field that looks like this. Subtracting the vapor fields leave this. And what you're seeing here, if you can even see this in the back, is consistent with this equation. Larger mixing is basically producing less water vapor, absolute humidity near the sea surface, and higher water vapor content closer to the top of the deeper boundary layer that you get when you have a greater mixing. So what's happening here is mixing applied to moisture is basically lofting water vapor to the top of the boundary layer, increasing the absolute and relative humidity, increasing the likelihood that convective activity will result. And so basically that's what's happening. Okay, so the mixing in the stronger mixing case is leading to larger relative and absolute humidity, more convective activity, and the convective activity is broadening the wind field. So let me quickly show you a schematic illustrating these two ways of modulating the storm size that I've tried to show you. Radius versus height. This cartoon is supposed to be the shape of the central dense overcast. Long wave warming is causing weak, gentle, but persistent lifting, and that's leading to convective activity. The other way that we had of doing this is mixing in the boundary layer, particularly moisture, as we showed in our paper. That is lofting moisture and when convectively favorable, leading to more convective activity. Then the convective activity is basically leading to a broader wind field because we have increased the heating in the outer core. Okay, so basically what was happening here is excessive moisture mixing in the HWRF PBL scheme was compensating for the lack of cloud radiative forcing. And so it was producing storms that were pretty good until they fixed the bug. Okay, then the storms were way too big, and so then the next approach there was to reduce the mixing. But the mixing was there basically inadvertently and somewhat fortuitously making up for the cloud radiative forcing bug. Okay, so let me continue. The horizontal axis here is eddy mixing. The vertical axis is height up to 2 kilometers. What I'm doing here is showing you profiles of eddy mixing averaged over a certain annulus and with various values of alpha. So we can see that if we stick alpha in this particular equation, it's going to do its job of reducing the eddy mixing so that as I make alpha smaller, the mixing gets smaller. But one thing you're noticing here, perhaps, is they all look like this. They all share the same boundary layer depth. The boundary layer depth, in addition to the mixing, may be important to this particular problem. Well, let's keep going. Further modifications were made to the HWRF GFS PBL in recent years. There was a wind speed dependent critical Richardson number added. My assessment is that had very little impact. A wind speed dependent cap on the eddy mixing that Peggy Boo and I inserted into the code in an attempt to try to get away from setting this alpha value as an external parameter with no true value. Okay. A mass flux-based non-local mixing, an adjustment of the alpha parameter near the surface layer. All of these things could have a small, medium, or large impact on the magnitude of the mixing, but they had almost no impact on the depth of the mixing. Now, this is relevant to me because I had been making simulations in parallel between HWRF and WRF ARW this entire time. And one thing I noticed is that other things being equal, HWRF always produced smaller storms. Okay, particularly once the cloud radiative, particularly before the cloud radiative forcing bug was fixed. Okay, and so what you're seeing here is a lot of the WRF ARW simulations use the YSU scheme. Okay, and YSU, other things being equal, is producing an eddy mixing profile that looks like this. It's based on the same K-profile idea, but the mixing is smaller, shallower, and located at a maximum closer to the sea surface. And this is all a consequence of the fact that YSU selects a shallower boundary layer depth given the same information, and everything scales with H. Okay, so if you look at this mixing profile compared to this, given what I have told you, you would probably expect, because this would end up with less moisture mixing, that other things being equal, it should produce a narrower storm, and in fact it does. Comparing the 10-meter wind field for these two simulations, the YSU is 37% smaller, going from smaller to larger. That's not as large as the impact in cloud radiative forcing, but it's still very significant. Okay? So basically for my second DTC project, what I tried to do is look more carefully at how HWRF can work with YSU and also another boundary layer scheme, MYNN2. Okay. The reason for starting with YSU is twofold. YSU is used in a lot of WRF ARW simulations. If you look at the WRF nameless page, it's actually recommended for tropical cyclones. I'm going to argue that you need to change that, by the way. And the other thing is that YSU and the GFS scheme are basically kissing cousins. They basically evolved from the same scheme, Troen and Mart. They're using the same equation. But there's a difference. There are a lot of differences between these two schemes. I'm not trying to say that those differences are relevant, but the single biggest difference is the critical Richardson number that they use to determine the first guess of the boundary layer depth. YSU uses a much smaller critical Richardson number, and as a consequence, other factors being equal, it ends up with a shallower boundary layer depth, and that means less mixing applied to moisture and other things. Okay? So basically it is that. I'm going to try to demonstrate that with this experiment using the HWRF model. On this side, I'm starting with GFS simulations. This is the operational model, and I'm taking, these are eddy mixing profiles averaged over an annulus, and I am decreasing the critical Richardson number that's used from the default and making it smaller, more like what is used in the YSU scheme. And what we see here is eddy mixing profiles as I decrease the critical Richardson number that becomes smaller in magnitude, and the mixing shifted down closer to the sea surface because everything scales with H, and H depends on the critical Richardson number. On the other side, I'm starting with YSU and starting with its default critical Richardson number, which is 0 for an unstable boundary layer, and increasing that. And now, as I increase that to make it look more like GFS, the mixing looks more like GFS. So the point here I'm trying to make is there are differences amongst these schemes, and some of these differences are important, but the most important difference between the two is the critical Richardson number that's used for the first guess of the PBL depth. Okay? And I think you could probably guess that the critical Richardson number is going to influence the depth and the intensity of the inflow in a similar way than alpha did. These are simulations, again, scaled radius out to 3 times the radius of maximum wind. The colored field is inflow, the bluer the stronger. When the critical Richardson number with the GFS scheme is set as it is typically in the code, this results in a storm that is relatively weak, and its inflow is weak and it's relatively deep. But reducing the critical Richardson number closer to what YSU uses results in a inflow layer that is stronger and much shallower. Okay, so there's a big influence there. Okay. So now, let me shift to some further evaluation of the PBL influence on tropical cyclone structure. I'm going to be showing you some slides that are very similar to what I showed you before, but I'm going to try to emphasize some different things here. This is based on the second HWRF-related DTC project, which has been in the last year. And what I'm trying to do with this is take the YSU scheme and get it working with the GFDL surface layer scheme within HWRF, okay? Testing that in my semi-idealized simulations, and also get MYNN scheme working with the GFDL surface layer in the HWRF model. Now, getting MYNN working in HWRF was a real chore, and if I knew what I was getting into, I wouldn't have bothered to start. Okay? But actually, I'm happy I did because I think I have some interesting things to show you. Okay? So first of all, this is, again, normalized radius out to 3 times the radius of maximum wind. The vertical axis is depth up to about 1.7 kilometers. The colored field is, again, inflow. The bluer, the stronger. The black contour is where the inflow is reduced to 10% of its maximum value. I'm using that as a proxy for the inflow layer depth. And superimposed in red are the eddy mixing produced by the GFS scheme as currently used in the HWRF operational model. Again, I'm averaging over a 24-hour period, averaging 360 degrees azimuthally. And what we see is that the maximum is about at 500 to 600 meters above the sea surface, and it's about 100 meters squared per second in this temporal and azimuthal average. This is the GFS scheme as used operationally. This uses what I call the CAP, The cap is what Peggy and I put in there. It was an attempt to try to restrain the mixing and keep it within the realm or the range of Jun Zhang's observations. This is what happens if you don't use the cap. Okay? So the eddy mixing field looks very similar, except it's definitely much, much larger in magnitude. And if you just focus on the blue field, it basically makes a big difference as far as the depth and the vertical wind shear within the inflow layer is concerned. The maximum inflow here, I'm scaling the inflow by the maximum inflow, and the maximum inflow is being reported to the upper right here. With the GFS cap, it's 24 meters per second. With the uncapped, it's actually even much weaker. So the mixing, very strong mixing, produces a boundary layer that is really deep. It has very little wind shear because the inflow is also weak. Okay? So this is what is being used operationally. This is what YSU does. Okay? So notice that the mixing is much smaller and the mixing is concentrated much closer to the sea surface. So in the back, you're just going to have to believe me because you probably can't see this. This dashed line here is marking 500 meters above the sea surface. I'm using that as a reference point. Notice all of these contours are basically below that level. That's YSU. I could also use MYJ, which is a very old scheme based on Meller and Yamada. It's an incomplete implementation of Meller and Yamada, but notice that it actually produces results that are pretty similar to YSU. Let me go back and forth there a few times and demonstrate that to you. So they're both producing mixing that's relatively weak and close to the sea surface. For some time, I thought that was actually a good thing that YSU and MYJ, being very different PBL schemes, were producing similar results. But I have decided since that both of them are wrong, and it's more likely that MYNN is better. Okay? This is what MYNN is doing. If you saw any of this stuff at the Tropical Conference, what I've managed to do since then is get MYNN working with HWRF. So these are HWRF results. And what we're seeing here is eddy mixing that is relatively large and located above 500 meters, extending up. This is radius of maximum wind equals 1, so that it's extending up into the eye wall updraft, but also becoming larger at relatively shallower radius in the outer core. So if starting with looking at out here, it's more like MYJ and YSU, and that has influence on the storm size through the vertical distribution of moisture. Other things being equal, MYNN2 produces smaller storms, more like YSU does, smaller than GFS. But within the eye wall itself, it's producing much more mixing, extending up into the eye wall. Okay, so that looks more like the operational model, but I think that it's actually producing this larger mixing within the eye wall for a completely different and incompatible reason. It's because that what MYNN is doing, being a more complete implementation of Meller and Yamada, it's basically producing more mixing where the shear is large and the stability is reduced. So this slide here is basically showing you what I just summarized, what I showed you on the past few slides. This is the operational model. The mixing is maximum about 500 or 600 meters above sea level. It's much larger if you don't cap it. YSU produces mixing that is much smaller and concentrated closer to the sea surface. Same is true with MYJ. One of the things you can do with YSU is increase the critical Richardson number. And if you do that, you get results that look more like GFS. And here's a simulation in which I increase the critical Richardson number a little bit. And notice it's sort of halfway between this one and this one. Okay, I'll refer back to this one in a minute. And here's MYJ. It's more similar to the operational one in terms of the strength of the mixing and the vertical extent within the eye wall updraft, but it looks more like YSU at larger radius, which influences the width of the storm due to eddy mixing. Okay, so let me finish up with some observational comparisons. I'm going to compare two results from two papers written by Jun Zhang and his collaborators. So you've seen this plot several times during this presentation already. Wind speed versus eddy mixing. The black dots are derived from Jun Zhang's observations. Basically, they show that at 40 meters per second, at 500 meters above the sea surface, we basically saw eddy mixing values from about 40 to 120 meters squared per second, and they should be increasing at some rate with respect to increasing wind speed. There are not a lot of observations here, but this is basically what I've been able to find, and we're going to use what we got. If we use the GFS scheme used by HWRF, but without the cap, it produces way too much mixing. At 40 meters per second, it's basically off the chart. But we knew that already, and that's why Gopal instituted that alpha cap, okay? If we look at YSU and MYJ, notice they're producing much less mixing when the wind speeds are strong. Okay, when the wind speeds are like 55 or 60 meters per second, it's only producing 20 meters squared per second of mixing instead of something that is maybe 10 times that. Okay, the reason for that is because the eddy mixing in YSU and MYJ is not only smaller, it's concentrated closer to the sea surface. These are observations of 500 meters. The maximum for the mixing in YSU is at 200 meters. So by the time you get to 500 meters, the mixing is pretty small. So this evidence suggests to me that YSU mixing is too shallow. Okay, it suggests to me that YSU mixing is too shallow. The operational scheme fits through this really well, okay? But it was engineered to do it, okay? Who did it? Me, okay? Okay, I plead guilty, okay? So basically, I'm trying to force it to fit these observations. If I didn't cap it, it would look like this, okay? So this was an attempt to retain the GFS PBL scheme and try to mitigate its problems by basically hitting it with a shovel, okay? So, but this is what MYNN produces, okay? So notice MYNN is actually looking very good compared to these observations, okay? So this is encouraging. At relatively larger wind speeds, we're producing larger values of mixing basically because there's more mixing at higher altitude within the eye wall because of the reduced stability and increased shear. So it looks more like what was being forced by the cap on the GFS scheme, but that actually could be coincidental. This could be producing better results for a more organically correct reason, okay? So here is a summary of the slides that I had just shown you. Again, wind speed versus eddy mixing. The black dots are Jun Zhang's observations. Now the red curve is what I showed you on the previous slides. That was using the winds at 500 meters averaged with respect to time and azimuthally. The gray area now shows you the values of eddy mixing with respect to wind speed using observation or using model data that has only been averaged temporally. I have not averaged it azimuthally. So it's showing me the variability about the azimuthal average. And what we see for uncapped, it's just way too big everywhere, no matter where you are, okay? For the cap, the cap is so strong it does not allow any variability about the azimuthal mean. YSU basically is just too small mixing at 500 meters, which is the only information I have pretty much everywhere. Same for MYJ. Excuse me. This is YSU with a larger critical Richardson number that allows the boundary layer depth to be larger. That increases the magnitude of the mixing and it increases the altitude of the mixing because everything scales with H. That kind of looks better, okay? And this is MYNN, which looks like it fits it very well, okay? All right. So let me show a few other comparisons. This is from a different paper by Jun Zhang. What we're seeing here is radius normalized by radius of maximum wind, again out to 3 times the radius of maximum wind. The vertical axis is height up to 1.7 kilometers above the sea level. And what is being contoured here for category 4 or 5 storms is the inflow scaled by the maximum inflow. So the maximum inflow is located right here, okay, about 100 meters above the sea surface at the radius of maximum wind. And it decreases to 10% here. I'm using that as a proxy for the inflow layer depth. And I'm just basically drawing a line that connects the maximum values at any particular altitude, and that gives me a vertical profile of the scaled radial inflow, which is here, which I can now compute from the model and compare for different PBL schemes. So if we start with the GFS scheme, Uncapped, it produces a profile that looks like this. This tells me way too little shear over too deep of a depth, but if we cap it, it looks a lot better. Okay, so it looks like it fits this black line, which I'm taking as truth, fairly well. Okay, and probably as good as it can get. Okay, let's look at YSU. YSU actually fits better. This was very encouraging. But remember, I think I've shown you persuasive evidence that YSU mixing is too shallow. But I can fix that by increasing the critical Richardson number. Why can't I treat that as a free parameter, particularly because I don't really know what I'm doing, okay? So I could just do anything I want, and that's why we do modeling, because we can twist anything we want. So let's twist that, and the results get worse. Okay, so the mixing may fit the mixing observations better, but the vertical profile of the inflow does not fit the observational composite as well. So that's telling me that basically the YSU may be getting the mixing better for the wrong reason. Okay, so finally, MYNN looks like it's nearly perfect. And what I like to say is it doesn't mean that MYNN is more right. It means that MYNN is less wrong, okay? So sometimes I get in trouble for saying this, but I want to just explain that a little bit. My idea is parameterizations are attempts at taking great complexity and making things as simple as possible and no simpler, okay? But along the way, we have to make a lot of trade-offs and a lot of approximations and a lot of compromises. And many of the compromises we make fortuitously are mistakes that cancel each other out, and it may be that what MYNN is managing to do here, and with the eddy mixing observations I showed you a few slides back, is get results that are more comparable to the observations fortuitously because it has perhaps made fewer mistakes. That's my idea. So I would like to try to bolster this with another of my favorite sayings. All models are wrong, but some are useful. Okay? So that's basically conveying the idea why I think that MYNN in this case is less wrong. So this comes from George Box, who was a famous statistician. He passed away a few years ago. George Box was actually talking about statistical models when he said all models are wrong, but some are useful. But I think it also applies to physical models and parameterizations as well. So let me summarize this. I've tried to show you that cloud radiative forcing and PBL, particularly moisture mixing, can profoundly influence the storm size. So we had papers in 2014 and 2017 about this, both in JAS. And basically, they both operate indirectly by encouraging outer convective activity. So we could also show you simulations where we make the outer core environment more hostile to convection, and then you can mix all the moisture you want or have all the cloud radiative forcing you want, and it doesn't actually make the storm wider because you are not provoking the convective activity. Okay. PBL mixing also significantly impacts the inner core inflow strength and depth. Seems to me that those are important things to try to get right, and it definitely varies with respect to PBL schemes. Okay. Our first DTC HWRF project basically demonstrated or was able to conclude that excessive PBL mixing masked the lack of cloud radiative forcing and HWRF's radiation scheme that they used then. So this did two things. It facilitated the adoption of RRTMG radiation in HWRF, which is still being used today, and we removed alpha as a free external parameter by computing it internally and applying a cap to it. That's still a kludge, but it's a kludge that actually makes the PBL scheme work a little bit better because of the fact that it's also no longer influencing the ocean outside of the hurricane and not influencing the boundary layer over land like the alpha approach was. Okay. Our second DTC visitor project was to implement and evaluate YSU and MYNN PBL schemes. This was I have implemented most of MYNN and HWRF. There's still more code to try to get working with the HWRF scheme or with the HWRF model. Modified both YSU and MYNN to work with the GFDL surface layer scheme that was considered a must by EMC because they put so much work in getting that working with tropical cyclones. And testing of MYNN is ongoing at EMC, and I just saw the first results results the other day, and I have to tell you, they're very discouraging. Okay. So chances are there's probably something else that's wrong that's going to do that. Okay, so anyway, I have a long list of thanks here. I'd like to acknowledge people who have funded this, including the DTC Visitor Program. Biswas and Catherine have been my hosts for these two projects. Peggy Boo and Kristen Corbacero are my co-authors. Legia has helped me with HWRF. Joe Olson has helped me with MYNN. Jun Zhang has helped me with observations. Sergio is testing the MYNN now at EMC. I thank George for letting me use his model. Greg Thompson and Brad Ferrier for discussions about microphysics. I'm sure I forgot someone, and that's all I have. So thank you for the invitation.
On the webcast.
Okay, Morris, the answer is no.
Well, my second question then is, you're showing very convincing sensitivities and explaining it really well for a single case, but hurricanes do vary in size from case to case. Have you looked at the ability of the various schemes in conjuring to reproduce the size variations for different environments?
Yeah, so of course, no two hurricanes are exactly the same. They tend to be small, medium, or large. They particularly tend to be smaller in the East Pacific than in the Atlantic. They tend to be much larger in the West Pacific. So hopefully, basically, once EMC is done testing this, we will see they have acknowledged that their current operational setup has a positive size bias, okay? So it's possible that MYNN will help that, okay? One of the problems that I've seen in my test, though this is not really germane to your question, is one of the things that HWRF does is it uses a longer time step for physics. It doesn't call physics like the PBL scheme every time step, which is what we typically do in WRF ARW. WRF ARW, oftentimes we won't call a cumulus or a radiation scheme every time step, but we'll call the PBL scheme every time step. My test basically showed that hurts MYNN, okay? It hurts YSU. Okay, it hurts them because it prevents the storms from spinning up as quickly in my idealized simulations. And I am kind of seeing that in the very preliminary results that I'm seeing from EMC. So one of the things that may actually prevent MYNN from being adopted, even if it produces better results and better structures and better vertical inflow profiles and better everything else, is the fact that it's too expensive. Okay, and in operational environment, sometimes fast is more important than good. Okay, and that's you can't let perfect be the enemy. Good, you can't. How does it go again? You can't let perfect be the enemy of the good, or something like that.
I think you just blamed EMC for all of our problems.
I did not.
Is there?
I have a simpler question.
Which version of MYN are you using in this test?
The version as of 3.9.
3.9.
Yeah.
Okay, well, that's probably pretty current. The other thing, I'm wondering if it's the case. I know YSU used to be mixing a lot. They produce a deeper boundary layer.
Yeah.
Not necessarily in terms of hurricanes. They study continental convection.
Yes.
We've looked at, for instance, over the United States compared to MYJ, YSU produce deeper boundary layer, drier boundary layer.
Right.
I wonder if it's their idea to bring down the mixing so that they more like the MYJ's mixing in some way. I don't know if that's Soyun's idea, but now that they actually brought it down, but I wondered if this kind of, for instance, tuning the mixing has a similar effect over continental convection, not just in hurricanes case, but
Yeah. Okay. So I think let me try to address it this way. My understanding, basically, both YSU and GFS evolved from the MRF scheme. Okay. So PBL number 99 in the name list, and MRF basically had the knock of producing PBLs that were way too deep and way too warm and way too dry. Okay, so along the way, several of the things that entered into YSU was basically an attempt to reduce the critical Richardson number, was an attempt to get a first guess of the PBL height that allowed it to basically, let me back up a second. So over deep mixed layer continental PBL over land, okay, you tend to produce a well mixed layer with a sharp inversion at the top of the PBL. Choosing a smaller critical Richardson number allows YSU to put the PBL top beneath the inversion, and that allows it to compute entrainment into the inversion, which it parameterizes based on surface fluxes explicitly instead of implicitly. So I believe that was the reason why the critical Richardson number was decreased. And what that does, by allowing it to compute entrainment explicitly, I think that is what helped it address the warm and dry bias and the deep PBL bias that the MRF scheme had. There are also differences with respect to the non-local mixing and the way that was handled, but I think the biggest reason was the moving from implicit entrainment in the MRF scheme to explicit entrainment in YSU, but the way that was basically handled was by reducing the critical Richardson number, which reduced the first guess, okay? That works, I think, very well over for continental situations. But there's really no reason to believe that the thermodynamic, basically a thermodynamic criterion for determining the boundary layer depth in a hurricane is even appropriate. So the real problem is that the K profile schemes probably have 2 strikes on them before they even step into the batter's box. Okay, so basically that's why I think moving to a scheme like MYNN is better, and it's really encouraging to see that it's doing better than MYJ. I haven't completely deconvolved all the differences between MYJ and MYNN, but MYNN has more terms, and it looks like some of those terms that are missing in MYJ are important, at least in the hurricane boundary layer, even if they're not important for the continental boundary layer. That was a really rambling answer, but I was trying to orbit around your question somehow. Yeah.
Well, this kind of question about MYNN. One of the problems with all these schemes is, one of the problems with all these schemes, as you've pointed out, is they have to define a boundary layer height. And
yes.
I know YSU is particularly dependent on that. What about MYNN? Does it care what H is? Or is H just a diagnostic?
I don't know if I can really answer that as definitively as I wish I could. MYNN does determine a boundary layer depth, okay? But I have not really played with it enough to really determine how it's being determined. So I need to become more of an expert on that. I don't think that it is nowhere near the Procrustean bed that the K-profile schemes are, okay? You know the story of Procrustes, right? He was the hotel keeper who decided that all of his visitors had to fit his bed. So if your legs were too long, he chopped them off. And if your legs were too short, he stretched you on the rack. This is exactly the analogy you wanted to hear after lunch, right? But the K-profile scheme is really a Procrustean bed because it's dependent on the determination of a boundary layer depth. And I tried to emphasize by saying repeatedly, everything scales with that. So if you get H wrong, you're already wrong. Okay, so it seems to me that other things being equal over the continental boundary layer, I don't really see that much difference or that much improvement or degradation between YSU and MYNN. There are differences to be sure, but they're not the same magnitude that we see in the hurricane boundary layer. And I think part of it is because the thermodynamic approach to determining the boundary layer depth, as shown in papers written by Jeff Keppert and others, probably is not the way to go.
Thank you.
You told that the MYNN didn't perform well with the HWRF cases, right?
Well, that's a very preliminary. All Sergio has done is a couple of cycles of Hurricane Maria so far. And it looks like, compared to the operational version, it is struggling to spin Maria up, which the operational HWRF was already struggling to get Hurricane Maria going. But Sergio is hopeful that since HWRF has a bias to over-intensifying weak storms, that might be addressed with MYNN. But if it doesn't get the big cases right, and if it can't do it economically because it's too resource intensive, that's probably going to be a killer.
Have you tried the YSU for real cases?
Well, actually, Sergio did. So it's an interesting story. I gave him the code last year, okay, and they tested it. And I got an email back from EMC saying they are really thrilled with how well YSU is working. And then they showed me some plots. And between you and me and the lamppost, I couldn't see a darn bit of difference between the skill. But they were happy with what they saw, and I was happy that they were happy. But 4 weeks later, I got another email saying they made more changes to the HWRF configuration, and now YSU is horrible. Okay. So it went from the hero to the goat in 4 weeks. Okay. So the short answer is yes, they're testing it, and the bottom line is it didn't make the cut for this year because the two primary things they did for H218 was increase the horizontal and vertical resolution, and I haven't quite parsed out why yet, but that hurts YSU. YSU particularly is hurt by increasing the vertical resolution.
So do you have any plans to work more on this MYNN/YSU
Okay, I'm sorry, can you ask that again?
I mean, do you have any more plans to work on this problem? Because now your DTC project is ending.
Well, I think that's going to depend on what happens next, what EMC's tests reveal. I expect that it will indicate that MYNN is good for some things and not for others, but there might be adjustments that we can make to the scheme that would improve its computational performance and its model skill. So I don't think I would count it out yet.
Any other questions? All right, let's thank Rob again.